We have done the most important things. Let's finish the other ensembles and go to examples that will clarify certain things. Let's continue with the canonical ensemble. Well, systems in which N, V, and T are constant. These are showing the equilibrium state of the system. Since your system is in exchange of energy with a heat reservoir, equilibrium will be determined by the common temperature, isn't it? The heat exchange will take place till the temperatures are the same, and the energy is variable in this. Energy is being exchanged. There will be some fluctuations in energy, although small. Well, probabilities of finding the system chosen at random from the ensemble, the system, to be in a state with energy ER is given by Boltzmann factor, isn't it, in this ensemble? We have done this, where beta is 1 over kBt. So the density matrix takes the following form: rho, N is rho n delta n, and we are still in the same representation where the density matrix is diagonal, and the diagonal elements will be these probabilities, beta E n, and 0, 1, 2, etc. Normalization condition gives you the constant as 1 over the partition function. This is canonical partition function, you remember, 1 over the cube, not the curly one. Partition function is nothing but the sum over all possible states. N or R is the same thing, doesn't matter. Density operator has the following form in this ensemble. Rho is Bryan-Cat notation, remember? So can be rewritten as 1 over the partition function, e to the minus beta h, Hamiltonian operator. And what remains is phi n, and this is the unit operator, as you might remember. Okay? So we have the form of the density operator, or the density matrix, is the representation. So it is 1 over the partition function, canonical, minus e to the minus beta h. Now this exponential of an operator should be understood as its expansion form this is the meaning of that exponential operator, isn't it? Okay. So the density operator is nothing but e to the minus beta h as an operator, trace e to the minus beta h. This is the general form of density operator in this ensemble. And if you want to find the average value of any operator or expectation value of a physical quantity, you can take average of this with a constant number of particles n, we are in canonical ensemble. In this case, you can write this as trace rho and operator, or 1 over q trace operator e to the minus beta h, or any average value can be written as trace operators e to the minus beta h divided by trace e to the minus beta h. So trace operator comes into picture when you want to take averages. In quantum mechanical language, find the expectation value. Do you have any questions for this ensemble, canonical ensemble, or density matrix in this form? Let's go to the last one and summarize that. It's very similar. Grand canonical ensemble. Well, we should remember that. In a natural calculation, that's what we do to get the average. And of course, the form of the density operator. Everything, I hope, will be clearer, a little bit more so, when I give you a specific example. In the grand canonical ensemble, the form of the density operator, which commutes with h, and the number operator, n, commutes with both of them, the generalization gives you the following. Well, this is the grand canonical partition function, e to the minus beta. Now we have both the Hamiltonian operator and the number operator. Okay? And rho commutes both with h, the Hamiltonian, and the number operator n, which gives you the number of particles in your system. Average value is 1 over the Q trace of the operator in question, e to the minus beta h, e to the beta mu n, number operators. Well, this is in explicit form is sum over n from 0 to infinity, z to the n, average value of the operator with constant number of particles, that is canonical ensemble average, isn't it? Times the canonical partition function divided by the grand canonical partition function. So this thing is nothing but canonical ensemble average. That's it. Let me take a specific example to make everything clearer. How to use these expressions to get the averages you are interested in. Let's take an electron in a magnetic field. What is an electron in a magnetic field? Did we do this problem before? Electron in a magnetic field problem? Well, the magnetic field will apply a torque on the magnetic dipole moment of the electron, which is the spin of the electron. Huh? So it will turn it in its direction. So there will be two states available for the electron, up and downstream, along the magnetic field opposite to magnetic field. That problem we have solved. It is paramagnetism, isn't it? So it will be nice to see if we get the same result in quantum mechanics as we did before. These are important. You have to understand these examples and relate them to each other. See how powerful is the statistical mechanics. Of course, instead of an electron, you should be discussing an electron problem and spin problem, isn't it? But let's take an electron in a magnetic field. Example. Consider the magnetic field in the direction of, in Z direction. Okay? Let's denote that by V. Apply it in the Z direction, or call the direction of the B as Z. intrinsic spin of the electron is shown by Pauli spin operators corresponding to the spin the magnetic moment in terms of EH bar over 2mc or magneton. There are two possible orientations, up and down. Spin 1/2 has 2s plus 1 orientations. 2 times 1 over 2 plus 1 is 2. There are two orientations, up and down, along the field and opposite to it. We know that problem. Hamiltonian is what? What is the Hamiltonian? Minus mu dot B, isn't it? Minus mu dot B, or minus mu B sigma dot B. Since B is in the Z direction, sigma is the sigma Z. So minus mu B, B sigma Z component of sigma. So it is going to be nice if we take a representation in which sigma Z is diagonal, isn't it? So Hamiltonian will be diagonal in that representation. We know that the representation in which makes sigma Z diagonal is the representation we want to choose because we want to diagonalize our Hamiltonian. In this representation, Pauli spin matrices have the following form. You can, of course, make a unitary transformation to other representations in which sigma x is diagonal or sigma y is diagonal. Okay? That means you can apply your field in any direction, or you can call the direction of your field any direction you like. Sigma x operator is this. Sigma y is 0 minus I. You remember this, okay? And plus I 0. And here's the diagonal sigma z, 1, 0, 0, minus 1. Okay. Density matrix, rho, let's take it in canonical ensemble. We know its form in that ensemble explicitly. Rho is e to the minus beta h trace e to the minus beta h. Trace is the sum over diagonal elements, which is the partition function. Okay. Hamiltonian is minus mu bb 1, 0, 0, minus 1 in this case, isn't it? with that sigma z. It is diagonal. Trace is easy to find, is e to the beta mu bb plus e to the minus beta mu bb. Remember the partition function? Sum over e to the minus beta en is exactly the same, isn't it? Two states against and along the magnetic field. Wonderful. So the density matrix has the following form then: beta mu bb plus e to the minus beta mu bb. Matrix form, that's also diagonal. Beta mu bb positive, zero non-diagonal elements, e to the minus beta mu bb. Okay? That's the matrix element. Everything is coming out perfectly clear. Now, expectation value or average value, if you like, of this sigma z operator. Well, what is this? It is going to be the magnetization along that direction, isn't it? Let's try to find it. The operator, then O is this operator in our formalism. This expectation value is going to be nothing but the trace of the operator with our density matrix. That's what we have found, isn't it? Let's multiply the two things. Trace, well, 1 over e to beta mu bb plus e to the minus beta mu bb. Two matrices are in this form, beta mu bb 0, 0 to the minus beta mu bb 1, 0, 0 minus 1. This is sigma z. The result is very simple. Multiply the two matrices, you get the following. This is just a number. If you multiply the matrices, e to the beta mu bb 0, 0 minus e to the minus beta mu bb you know how to multiply matrices. That with 1, this is 0. Okay, that with 0, with minus 1 brings that Well, trace is the sum of diagonal elements, isn't it? Very easy to take. We know the matrix. So the result is trace, sum of diagonal elements, divided by that number, plus sign. Well, it is nothing but tangent hyperbolic beta mu bb. That's the result. Do you remember tangent hyperbolic function? Yeah, exactly. Recall paramagnetism problem I solved for you. I found m and mu tangent hyperbolic mu b over kbt. Exactly the same result. Do we have any questions up to now? Anything? So, what should you see in what we are doing? First, I'm giving you the basic formalism, then applying it to a specific problem, isn't it? That specific problem is the model we apply our ideas to. So you should do the same. For each topic, you should ask yourself, what is the basic definitions and rules in this part of the problem? Then, knowing the overall picture, apply it to a specific physical problem. That problem is exactly as I did in the class. Could be a classical gas or a quantum gas in 3 dimension, 2 dimension, and 1 dimension. Isn't it? It could be a gas, and later when we discuss the interactions, it could be liquid or a solid, a piece of material, or a system of electrons or bosons. As you are going to see, it could be a star in the sky, like a white dwarf, or a nucleus, nuclear matter. So we can apply our basic formalism to any physics problem we want, if we can model it. Simple models can be used to describe that physical system. Okay? That's what you should remember. What is the basic formalism and how I can apply it to the physical problem given to me. Let me give you one last example. We have just enough time for this. particle in a box. Nice, isn't it? You have solved it, I don't know, 1,000 times. But what about the average values associated with a particle in a box? Is it a simple problem? I don't know. We have to see the problem. Here, in this case, what is the physics? What are you going to take for the Hamiltonian? It is not minus mu dot B, like particle in a magnetic field. What is the total energy of a particle in a box? If the walls of the box have infinite potential, it is not going to be tunneling into outside. It will be inside the box, and the potential energy will be zero, can be taken to be zero. It will be all kinetic energy, isn't it? P squared over 2m in the box. Remember, we have to know the Hamiltonian in this quantum statistics. Let's do it, since the simplest we can get. Well, the next problem will be what? Harmonic oscillator, of course, which is done again 1,000 times up to now. Pedagogical examples. Well, that may take you to a gas, many particles in a box, but this is a single one. Hamiltonian is simple, P squared over 2m, or P being IH bar del operator. In quantum mechanics, it is h bar minus h bar squared over 2m del square as an operator, and that's always positive, isn't it? Kinetic energy is always positive. Although there's a negative sign there, when you take that square, you get positive quantity. Eigenfunctions, we can, in the energy representation or position, it is one over square root volume, normalization constant, plane waves, it's a large box, let's say. Boundary conditions are as follows in all directions. If you go with the side of the box to the other face, you get back the same wave function as you go in other directions. Well, you may look at it in different ways. If the particle reaches the other phase, it reappears again in the first phase. So it goes back and forth. Eigenvalues are to be found as h bar squared k squared over 2m. Remember this solution? Of course you do. K wave numbers are quantized well in units of 2 pi over L. You remember that result, and quantum numbers can be written as nx, ny, and z, or in general, if you want the vector notation, you can show it as like this. Each one of these are x component of k, for example, is 2 pi nx over L. Same with y and z. These are integers. Plus minus 1, well, 0 is also there, plus minus 2, etc. So they can be positive, negative, and 0. This is quantization. Well, let me underline one more thing. I did this before, but it's extremely important. Energy levels are quantized only if the particle is confined to a space, in space, to a small region. Coulomb interaction, attraction of a positive charge of the electron in the case of atoms, confines the electron into a Bohr radius, 0.529 angstrom. Now that's the reason for quantization, isn't it? If you take that region very large, you don't have any quantization. Those states become continuous states. Okay? Difference between energy levels are quite small. Now let's look at the density matrix for this problem then. Very pedagogical problem, I think. Very useful. In this case, here is our density matrix or operator. Well, this is also known as coordinate representation, shown as so we are going to talk about probability of finding the particle at a position at a specific point in the box, isn't it? This is R e to the minus beta h trace. Well, since that is a number, operator is up in the numerator, so it is R e to the minus beta h R prime that is to be written as, these are wave functions in that representation, coordinate representation, corresponding to a specific energy as a function of position, e to the minus beta e R prime. Or it is a sum and these are nothing but the wave functions. Huh? So this quantity requires a summation. Energy is determined by K, wave number, wave vector if you like. So it is 1 over L cubed, given the form of these wave functions. It is a sum over K exponential minus beta h bar squared t squared over 2m, the kinetic energy term, and cross terms, of course, e to the I k dot r and r prime, plus I k dot r minus r prime. Now, as usual, and as I discussed before, summations in this form can be transformed into integrals by using the density of states, isn't it? So A summation over K is, well, density of states now. This time we shouldn't mix up rho we used for density of states before. You can change this into an integral by using density of states. What was density of states in this case? Well, we can turn that into an integral. What was density of states? Do you remember? V over 2 pi cube. V over 2 pi cube over K. So it is V over L cube. They will cancel. They are the same thing. Integral exponential minus beta h bar squared k squared over 2m plus I k dot r minus r prime d cube k. Sum was over k, so integral will be over k. Can you show this integral? Again, a small homework for you. To be in this form, m over 2 pi beta h bar squared 3/2 exponential minus m over 2 beta h bar squared r minus r prime squared. Okay? So it is a Gaussian function. Let's take the trace to get averages. For the partition function, single particle partition function, we have to take the trace of e to the minus beta h. That is nothing but the partition function, isn't it? Okay, let's do that. It is R e to the minus beta h R diagonal element d cube R. We have done this. It is V times M over 2 pi beta h bar squared 3/2. Check this, okay? This is nothing but one particle partition function, canonical, and it is Q1 beta, and nothing but V over lambda T cube, isn't it? Check it. Matrix elements of the density matrix this is exactly what we have found before, isn't it? When you look at this, if you look at the diagonal elements, you can find that this is proportional to the probability of finding the particle in the vicinity of R in the box, isn't it? When R equals R prime, it is 1 over V. Probability of finding the particle inside the box is given as V, isn't it? So, normal. Symmetric between states R and R prime. And off-diagonal elements R and R prime of rho is spontaneous probability of spontaneous transition from R to R prime in the box. So, one important thing that you should do, what is the expectation value of the Hamiltonian? It's nice to do this. I'm not going to bother, but it is minus h bar squared over 2mv integral del squared exponential written above, this one, this del squared at r equals r prime d cube r. This comes out to be, when r equals r prime, exponentials will disappear, 3 over 2 beta, and it is 3 over 2 kbt. Is that what you expect? Yes, it is like a gas in a box. If you have n particles, you have 3 over 2 n kbt for the energy. For a single particle, it is exactly this. So I advise you again to look at the formalism. How are we going to calculate the average values using the density matrix? And that takes us to the statistical mechanics from there. Do you have any questions? Are you happy? Thank you.